Hello, my name's Harper. I'm going to be talking about my game Mouse Maze. So we're going to start off with the continue button. I've already completed a few levels, so when I press continue, it's going to put me back into level 4. We spawn in when we touch the red square there, and then once we reach the green square, all the way around here, we will finish the level. Depending on how many coins we collect and how many deaths we have, we will get more or less score. So here we see we got 13 score. Because we're on continue, it puts us straight through to the next level. Right, next I'll talk about level select. So you saw we just finished level 4, which means we've unlocked level 5, and I can play this level. I haven't completed level 5 though, so if I try to play 6 through to 8, I can't do it. Now we're on to level 6, and another thing, every time you die, there's a little blood splatter there. Next, the high scores page. So you can click here. You can see all these scores. These are stored in a hash, and they're sorted by the value from largest to smallest, and you can upload your own score here. Finally, settings. Here's where you can choose your skin, and depending on how many levels you've completed, you will unlock more skins. If I go back and complete another level, you will notice I unlock a new skin here. One last thing, score is only calculated on your first time completing a level. So for example, if I try to go back to level 3, you see there are no coins here available to collect. And if I finish the level, there is no impact on score, even if I have multiple deaths. Up here we have modular decomposition with the layers, and there is functional decomposition throughout the entire program. So everything is in a function. The code is data driven in a lot of places. I'll focus on just this one here. So we use the level select coordinates calculator, which takes in an amount of levels. And then up here, it will return the coordinates where each of those levels should be put on the screen, depending on how many we need. And it returns an array with all of those values. So it returns different values for more or less levels that it needs to calculate coordinates for. And we've got coupling and cohesion throughout the entire code as well. But for example here, levels finished is passed through a level, calculate score also passed through a level, square area clicked is calculated, it is passed through coordinates, etc. Now I'll talk about my custom project. So for this, I researched sorting algorithms. Yeah, we've got our contents page here. Just a quick introduction. The methodology. So here I talk about some key terms, big O notation and benchmarking, which I used to complete my own experiments. Some things I had to research here. I had to do a lot of research with big O notation. It's covered a little bit in one of my other subjects, but not enough. And I also had to research things like case-ordered arrays, stability, space complexity, etc. This next bit here, I talk about the 4 sorting algorithms that I used in my experiments. So we just give a quick rundown of how the sorting algorithms function, along with some pseudocode and the big O notation to go with it. So insertion sort, merge sort, and quick sort, and bubble sort was just up there. And additionally, I also talk about the built-in sorting algorithms that are used within Ruby and Python. So Ruby uses the quicksort and Python uses the timsort. With the experiments, the scope and hypothesis just lay out the grounds of the experiments, how they're going to be conducted and how they're going to remain fair. So for example, only use Geeks for Geeks code where applicable, because I could write some of these algorithms, but they tended to be a bit slower than the proper code. Now for the results. So the first test, I tested all 4 sorting algorithms from 10 items to 100,000. And as you can see, the bubble and insertion sort were very slow. And also I found it very interesting that the graph corresponded to the predicted big O notation chart. And next with this bit, I just put it on a split graph so you can see the true scope of how slow the bubble and insertion sorts actually are. Next, I tested all 4 sorts with much smaller arrays, so 5 through 50. And you can see here that the insertion and bubble sort perform much better, but still not quite as good as the quick sort. This next bit, this was really interesting for me. We talk about k-sorted arrays. So to generate these arrays, I used a shell sort and just modified it a little bit so that it would not completely sort each array. And the insertion sort and bubble sort, as you can see, perform really well, especially compared to how they performed before. And the merge and quick sort, as you can see in this graph down here, have no change in speed. Next, I talk about the different criteria that you might think about when choosing a sorting algorithm to use. So for example, if you are sorting a k-sorted array, you might lean towards an insertion sort. Next, I talk about my personal decision-making process in choosing a sorting algorithm for my custom code mouse maze. And we have a conclusion, our references, and also an appendix here with some unrelated experiments. I've also included the Excel spreadsheet that I used for my experiments, so you can see some of the raw data as well as some of the graphs that weren't included.